Okay, we are working with the Kinetics notes that are in the Unit 9 Notes Google Drive folder. I'm going to start with those, and then for the very first lesson, we're going to then also work with the, it says Unit 9 Day 1 practice problems. So we'll go to those after we finish the first part of today's lesson. So kinetics is the study of rates of reaction. So how fast or slow do reactions occur? How do we measure that? How do we express and communicate information about that? So that's kind of where our focus is going to be. So the first thing we want to look at is, all right, what has to happen for a chemical reaction to occur? And the basis for this is something called collision theory. And collision theory has three basic parts. It says that in order for a reaction to occur, that the reactants must collide, that the collision has to have sufficient energy, and we've looked at this back in the last unit when we looked at the energy diagrams, and we talked about something called activation energy. So when we're talking about that the collisions have to have a certain amount of energy, that's the activation energy for the reaction. And then also, it's that the reactants, when they collide, they have to have the correct orientation. So that just means that the way in which they hit each other, like which end of the molecule collides with a certain end of the other reactant molecule, that makes a difference. So not every collision, even if it has enough energy, will progress to create products. They also have to hit each other in the right way. All right, so this is kind of a little bit of review, but it's been a couple of weeks, so let's take a look. Here's our energy diagrams, and so we're looking for, we've got potential energy on the Y, and then our reaction coordinate, or reaction progress, is on our x-axis. So if we look, which represents the potential energy of the product? So we're assuming that this is our 0, and so remember that our products are here, and whoops, what happened there? And our reactants are here. So line E represents the energy of the products, all right? The potential energy of the activated complex. Remember, that's kind of like an intermediate state that is where the reactants have started breaking bonds and the product bonds are starting to form, so it's like an intermediate state, and that is at the top of the hill. So up here, this is our activated complex. And so letter C would be that one, and then the potential energy of the reactants, that would be letter A. The activation energy, that is the energy from where the reactants start up to the top of the hill, up to where the activated complex is formed. And so that's represented by line B. And then the heat of reaction, that's our enthalpy, or delta H, and that's the difference between the products and the reactants. So F represents that amount of energy. And then here, because our products have a higher energy value than our reactants, that indicates that that is an endothermic reaction. Now the reverse reaction, that's if we're starting on the right side and working our way to the left. So essentially our products are now our reactants, and the reactants are now the products. So the activation energy of the reverse reaction is from the products to the up to where the activated complex is, and so that's letter D. And then it says which letter indicates the heat of reaction of the reverse reaction. Okay, so that is still going to be the same, because remember our enthalpy or delta H of the reverse reaction is going to have the same magnitude, because it's still the difference between products and reactants. It's just that the sign would be opposite. So we're still, letter F still represents the size of that change in energy. And then the reverse reaction, where we're starting, is at a higher energy than where we end up, so that means it is exothermic. Okay, we didn't go over this part in class, but in the event that you wanted to just use this to kind of make sure that you're good to go with these energy diagrams, let's just go ahead and I'll fill in the answers for this. So reactants of the forward energy, it's about 80, and the products is about 160, and the activated complex is right around 240. Activation energy of the forward reaction is 240 minus 80, so that's about 160. The delta H is going to be 160 minus 80, so it's about 80. The forward reaction, again, this one is endothermic. And the heat content of the reactants of the reverse reaction is about 160. And the heat content of the products is around 80. The heat content of the activated complex for the reverse is still 240. The activation energy for the reverse is going to be 240 minus 160, so that's about 80. The heat of reaction, or delta H of the reverse reaction, is going to be, products is 80, reactants is, so products 80 minus 160, so that's going to be a negative 80, and the reverse reaction is exothermic. Okay, so we're going to kind of use these questions to go further into our introduction of reaction rates. So chemical reactions occur when reactants collide. For what reasons may a collision fail to produce a chemical reaction? So remember we said if it has, okay, so, whoops, I don't know why it did that. Not enough energy. Or also if it has the incorrect orientation. If every collision between reactants led to a reaction, what determines the rate at which the reaction occurs? Okay, so that means if every collision, so if we did have enough energy and we did have proper orientation, then the rate is solely going to be based on the frequency of the collisions. So more collisions in a given amount of time means we're going to have more reactions. So what is the activation energy of reaction, and how is this energy related to the activated complex? The activation energy, that is the energy needed to get the reaction started. That is the minimum energy that the collision has to have. So if we remember from our energy diagram, so that's going to be this amount of energy right there. And so it's the energy that is required to create that activated complex so that the reaction can go forward.
we're going to talk more in detail about catalysts, which is brought up in number 4. But essentially, a catalyst, it increases reaction rate by providing a pathway with lower activation energy. Okay, and so that means that more collisions will go forward and create products. All right, so 4 things that will speed up or slow down a chemical reaction. So changing the temperature, because changing the temperature is going to change the kinetic energy of the particles. So changing the temperature will affect the frequency of the collisions and also the energy of the collisions. So raising the temperature, we're going to increase the frequency and the energy of the collision. So that would speed up the chemical reaction. The other thing is the concentration of the reactants. So we can change the concentration by either adding or removing reactants. Or the other thing that we can do to change the concentration is we can change our volume. If it's gases or if it's, say, a solution, we might change the amount of solute. So that can also change the frequency of the collisions. The other thing we can do is we can change the surface area of the reactants. And by that, I mean that if we, for example, grind the reactants up into a powder, that increases the ability for the reactants to interact with each other, which means we're going to have more collisions. So a greater surface area is going to speed up the reaction. And then the 4th thing, which we mentioned before, is that the presence of a catalyst will also change the rate of the reaction. All right, again, this is just for the review purposes, since we've done these energy diagrams before. But it says we want to draw a energy diagram where it has the energy of the reactants is at 350. So we'll put it up here at 350. It's going to come in like this. It's going to go up, and then we're going to come down, and I'm sure this is not, my scale is not great on this, but that would be 250 for the products. And then if the activation energy is 100, that would put this at the top of the hill at 450, because that would mean I have a 100 between my reactants and the top of the hill. And it says, is the reaction endo or exothermic? It is exothermic because the products are at a lower energy than the reactants. Okay, how could you lower the activation energy? That would be by adding a catalyst. And so let's do this. So say we're gonna use a red line to show if a catalyst is added. So essentially what adding a catalyst will do, all right, is it makes the hill smaller. All right. Note that it does not change the value or the energy of the reactants or the products. All it does is it just affects the size of the hill in the diagram. Okay, so a couple of things about this particular page here. One thing to note is this, that's why it's written so large here. Reaction rates are determined experimentally. We do not use the balanced equation to actually come up with a rate of reaction. We use experimental data, and a lot of what we're going to be doing in this unit is taking data and figuring out reaction rates from data. So in looking at the rate of a reaction, here's a graph, and it's showing the change in concentration of the reactants over time. And one thing to note about this is that the change is not linear. And that's because as the reaction progresses, we are decreasing the number of reactants, which means the rate of the reaction is going to slow down because the frequency of collisions will be less because we have fewer reactants to collide with each other. That being said, whenever we are defining a rate of reaction as like our change in concentration over change in time, that is an average. Okay, the rate at any given point in time would be based on our slope, right? The slope of the line that's tangent to that point on our graph. That would be what we call our instantaneous rate. Okay, but most of the time we're looking at a specific amount of time and looking at the change in concentration over that time, which is really an average. But one of the things to note is that if our change in time occurs kind of up here at the very beginning of the reaction, then it's as linear as the curve can possibly be at that point. And so we can get pretty close to an instantaneous rate of reaction with that approximation taken at the beginning of it. One thing to note here is that if we're talking about expressing like a rate of change of the reactants, that we use a negative symbol for that. And that just means that it's decreasing. Whereas if we're talking about the change in the product concentrations over time, okay, we're going to use a positive value for that. So the negative, if you see where it has rate equals negative and then a number, the negative just means that we're dealing with a reactant and that it's decreasing. Okay, so again, this is just clarifying that when we talk about average reaction rate. Now, one thing to note is here, right? Remember we did those brackets? That stands for molarity, right? And remember that we said molarity is equal to moles per liter, okay? And then delta, again, delta is always final minus initial. So the change in my molarity over the change in time is what we're dealing with when we look at our average reaction rate. Now, the one place that we will use our balanced equation is if we're looking at relative rates. So this would be where I have used experimental data to find the rate of change of one of my reactants or products. And in this case, so this example, we've gotten through data that the change in concentration of the ammonia over time is about 3 times 10 to the minus 6 molarity per second. And it wants to know, well, okay, what is the rate of disappearance of the hydrogen? Well, let's look at, and I'm going to rewrite it down here. So 3H2 plus N2 yields 2NH3. So in thinking about this balanced equation from the standpoint of how fast concentrations are changing. So this tells us that I need 3 hydrogens. I need to consume 3 hydrogens to make 2 ammonia molecules. And I need to consume one nitrogen molecule to make two ammonia molecules. And so our nitrogen is going to be changing its concentration slower than the ammonia or the hydrogen. And the hydrogen, its concentration is going to be changing faster than any of the other things in this reaction. So we can use our balanced equation as a ratio. Okay, so if I have 3 hydrogens to 1 nitrogen, so just like we've been doing with other ratios, and the nitrogen I know is 3.0 times 10 to the minus 6 molarity per second, and so I'm solving for what the hydrogen would be, and oh, that's ammonia. Hang on there, that's ammonia, not. So let's fix that. There we go. All right, so let's try that again. So 2 ammonias, there we go. Now, so we have that our x is going to be 4.5 times 10 to the minus 6 molarity per second. So we can use the coefficients in the balanced equation to find the rate of change of one thing versus the other. And so we would reflect this as that the delta of the concentration of the hydrogen over delta T is going to be a negative 4.5 times 10 to the minus 6. And that's, again, molarity per second. Okay. So now we're going to talk about something called a rate law. And we're going to be dealing with 2 different kinds of rate laws. One is looking at how the change in how the rate of a reaction depends only on the concentration of the reactants. And that is called a differential rate law. And we're going to talk about those first. Then we have something called an integrated rate law. And with the integrated rate law, the difference is that there we're going to look at how the change in concentration relates to the change in time. So we're going to enter time as a factor. So let's look at our differential rate law. We're going to start with that. So it has the form of rate equals K, which is our rate constant, and then we have the molarities of however many reactants we have. And each reactant is going to be raised to a power that indicates its order. And what the order is the order gives you a measure of how much does changing the concentration of this reactant affect the rate. And so if we have something that, say, has this changing it affects the rate in the same way it was changed. In other words, if I double the concentration of a reactant and that doubles the rate, or if I triple the concentration of a reactant and that triples the rate, we call that first order. Okay, so first order, I kind of think of that as same. So if it's first order, and we'll look at, I'm going to make a little table. So reactant concentration versus the rate. And so for first order, I just call that same, meaning if I double it, it doubles the rate. If I triple it, it triples the rate, and so forth. Now, second order, okay, whatever I do to the reactant concentration, the effect on the rate is that squared. So if I increase by 2 the reactant concentration, it's going to increase by 2 squared, or 4. If I increase by 3, it's going to increase by 3 squared, or 9, and so forth. Okay. Now we also have something that is called zero order. Zero order means that whatever I do to the reactant concentration, it's going to have no effect at all. And in that case, it doesn't even show up in the rate law. Okay, so any reactants that are not present in the rate law, that just means they are zero order. And a phrase that you'll see in some of our quest problems are, it will say that the rate of reaction is independent of the concentration of that reactant. Okay, so the gist of this is that not all reactants are equal. There are some reactants that you change them and you get a much bigger boost in your rate than changing the concentration of others. Okay, so again, here's an example. So looking at this, we have that the rate equals K, and then the nitrogen monoxide is second order, and the hydrogen is first order. Another thing to note here, this is determined experimentally. And so the fact that the NO has a 2, that it's second order, has nothing to do, it's just a coincidence that in the balanced equation it has a 2. And you can again emphasize that by looking at the fact that the hydrogen is first order, even though it has a coefficient of 2 in the balanced equation. So coefficients in the balanced equation do not correspond to what order the reactant is. All right, so now let's look at this thing called the rate constant. Again, our rate constant, and that's one of the things you have to be careful with within the problems, is that when you're reading the information they're giving you, be very clear about, are they giving you a rate of reaction or are they giving you a value for the rate constant? Okay, so pay close attention when you're reading these and make sure you're clear on what it's giving you. So here I have, we're using the rate law from before. And one of the things to note is that the units for the rate constant they vary. And the thing that we want to think about, and I'm going to rewrite this over here, is that the rate of reaction, that's always going to be the molarity over some unit of time. Most commonly, it's per second, okay? But it's just a molarity divided by time. And so we're going to, this one, it's looking at seconds. So it has to be that, all right? And then these things with the brackets, right? These are molarities. And so for this given example, I have a molarity squared times another molarity. So that gives me in this equation that I have a molarity cube. So the units for K are whatever they have to be so that when I multiply the concentrations of the reactants with K, that my ending unit is molarity over time, and in this case, molarity over second. So given that I'm multiplying K by molarities, K is always going to have a time unit in its denominator. So in this case, I got to put the second there. There's no other place for it to come from. And then the other thing that K has to do is it has to cancel out all but one of the molarities. So in this case, I have molarity cubed, and that means that in the denominator, I have to put molarity squared because I want to cancel 2 of those 3 molarities there. And so when I multiply 1 over seconds times molarity squared times molarity cubed, I end up with molarity over seconds, which is the unit for the rate. All right. There are a couple of different ways that you will see this expressed. So here's the way that I wrote it in when I was working through the example. But you might also see it written this way, because if molarity is in the denominator, molarity is moles per liter. So if it's in the denominator, it's liters over moles. And in this case, it's squared. So we would have liters squared over moles squared, and then times the seconds in the denominator. Or the other way we can write it is molarity to the -2, which is the same as 1 over molarity squared, and then s to the -1, which is the same as 1 over seconds. Okay, so let's take a look at an example problem here. So here I have some wording that says the rate of reaction doubles when either the concentration of iodide ions is doubled, while we keep the persulfate constant, or when the concentration of persulfate ions doubles. So we're going to go down to the second, or part B first, in that we have iodide and we have persulfate. And because it's same, I double the reactant, it doubles the rate. In both cases, they are both going to be first order, which means my rate law is going to be rate equals K, then iodide with no superscript, and then S2O8 with no superscript. The overall order, which is down here in part C, is just you add up all of the individual orders of the reactants. And so in this, I have 1 plus 1, so my overall order would be 2. Okay, right, looking at this, here I have 3 reactants. So I have bromate, bromide, and H plus. So it is, based on this rate law, it is first order in bromate, it is first order in bromide, and it is second order in H plus. Our overall order is going to be 1 plus 1 plus 2, or equals 4. Okay, so right here in the notes, this is where we're going to pick up on day 2. So now we're going to jump to our extra practice in here. Okay, so let's look at this. So we've got, all right, we have, it wants, write the rate expression for that reaction. Okay, now, rate expression, that means we're writing relative rate expressions. So here, if I say minus delta N delta T, all right, then I'm going to write everything in terms of how it compares to the change in concentration of the nitrogen. All right, so the nitrogen has a 1. The hydrogen is 3 times faster, so that means the rate of the nitrogen is going to be 1/3 the change in the hydrogen. And then it's a reactant, so that's going to be negative as well. And then it's going to be 1/2 the change in the ammonia. All right, so number 2, we got to balance our equation first. So here I need a 3 and a 2 and a 2. Let's make that a little bigger here. All right. And it says we want the rate of disappearance of the KClO3 if the rate of appearance of the oxygen is 4 times 10 to the -2 molarity per second. So again, if we know the rate of 1 that was determined experimentally, I can use a ratio to find the rates of anything else. So here, 2 KClO3 to 302. And then the oxygen is 4 times 10 to the minus 2 over x. And so x is going to be 2 times 0.04 divided by 3. So that's going to give me 2.67 times 10 to the minus 2 molarity per second. Okay. And again, here we have our what is the general rate law. And again, if they're not giving you data, they're wanting that relative rate expression. So this would be minus delta H3BO3 delta T is equal to minus 1/3 delta HCl delta T is equal to change in the boron trichloride delta T, which is equal to 1/3 the change in the water delta T. Okay. All right. Number 4, what would be the rate law for a zero order overall reaction? Zero order means the reactant does not appear in the equation, so that is rate equals K. And what that means then is that the rate of the reaction never changes. No matter how the concentration changes, it still proceeds at the same rate. Okay? It says name one factor that can increase the success of reactant collisions and explain how it increases the reaction rate. Well, I think the most obvious one is our temperature. So if we increase the temperature, that does actually two things, is that it increases their kinetic energy, all right, which is going to increase my collision frequency. And then it's going to, by increasing the kinetic energy, it's also going to increase collision energy. Okay, so here it says our rate constant, all right, so that means this is, change colors there, that's our K. The concentration of the nitric acid is 0.05 and the ammonia is 0.1, and both reactants are first order. What will the rate of this reaction be? So I highly recommend that you always write out the rate law because it will help you keep your focus, and typically you're going to get a point on a free response question for writing the correct rate law. Okay, so here is my equation. I'm going to plug in my K. I'm going to plug in the nitric acid, and I'm going to plug in the ammonia. And that's going to give me 0.5 times 0.05 times 0.1. So I get 0.0725, and that unit would be molarity per second. Okay. Now, in this next one, we get that the rate law for the following reaction rate is rate equals KH2F2. Okay, so it's first order in the hydrogen, first order in the fluorine. And here the thing to note is it's giving me two sets of data. So it says the rate is this when these are the concentrations, and then it's asking me to calculate the rate when these are the concentrations. So the first thing I'm going to do is I need my K. If I'm going to calculate a rate, I got to have the rate constant. And note that for the same reaction, the rate constant will be the same as long as we are running the reactions at the same temperature. So temperature is the only thing that when we change it, it will change the rate constant. Okay, so again, I'm going to rewrite this. Rate equals K H2F2 2. All right, and then, so I have a rate 3.15 times 10 to the minus 4. That's going to equal K 0.084, and then the fluorine is 0.25. So 3.15, 10 to the negative 4th. And I'm going to divide by 0.084 and 0.25. So I'm getting that K is 0.015. Now, because it is, we got molarity squared, it's going to be the units 1/seconds times molarity, right? This is a key point. On the AP Chem exam, whenever they ask you to find a rate constant, always, always, always put the units, because it is almost always a second point. Like that is almost always a 2-point question. You get one for the value of the rate constant and then one additional point for the units. So don't cheat yourself out of that additional point by just not putting in the units. All right, so now I've got my K. So now I'm going to go over and we're going to do this again. Rate equals K H2 F2. And we're solving for the rate now, because now I know my K value. And then it says now the hydrogen is 0.039 and the fluorine is 0.099. And so that gives me 0.015 times 0.039 times 0.099. So that gives me 5.79 times 10 to the negative 5th molarity per second. So that would be my final answer for this question. Okay, one last note that is what you will see in some of the, well, no, wait, we'll keep going with these questions, but I wanted, while I'm thinking about it, is that in some of the quest problems and in some other problems, you will see where they give you a rate for a reaction, and it's not, it doesn't specify that, oh, this is the rate of change for this reactant or the rate of change for this product. It just gives you a rate for the reaction. So say I have A plus, or 3A plus 2B yields 7C, okay? And it says the rate is 5 times 10 to the minus 2 molarity per second. It just says that's the rate. Okay, what that is that is the rate for what they refer to as a reaction mole. And what that is that this rate is if there is a reactant or product that in the balanced equation it has a coefficient of 1, then this is its rate. Okay, and what that means then is if I want the rate of change of anything else that has a coefficient, I'm just going to multiply it by that. So let's just look and see. So delta, the change in A or change in time, that would be, and it's going to be negative because it's a reactant, so negative 3 times the 5 times 10 to the minus 2 molarity per second. And if it wanted the change in B over the change in time, that's going to be negative 2 times 5 times 10 to the minus 2 molarity per second. Okay, so that's just kind of explaining, again, some of the ways that you will see these questions presented to you or get this information there. All right, so let's keep going with our problems here, because this is another one you'll see some quest problems like this. It says if the concentration of a reactant is doubled and the corresponding rate quadruples, what is the order with respect to that reactant, it is second order. Remember, if I double it and it times 2 squares is the effect on the reaction rate, then it's second order. All right, this is what are the units of the rate constant if the rate is, so here I have molarity times molarity squared times molarity. All right, put all that together, I've got molarity to the fourth. So my K unit, first off, it has to include the time, and it has to cancel all but one of my molarities. So it's going to be 1 over seconds molarity cubed. So option E. Okay, I think that is all. And so that concludes our day 1 lesson.